Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today, we are starting a new section by diving into integration. We'll be looking at what integration is and Riemann's definition of it. So if you're ready to learn, then let's get into it. The idea of integration arose from intuitive ideas about area and volumes in geometry, and we'll see how integration gets to those stages later on. But for now, if we just look at Riemann's definition or Riemann's sum, we can think about what is the area A, so this whole area represented by A, under a curve f of x between the ordinate values x equals A and x equals B. How could we work out that area A? So the way of working out this area under the curve, we could start by imagining a large number of strips, so each one of these rectangles is a strip, and summing up all of the areas of each strip together. So if we imagine each strip is between x0 and x1 is the first strip, then x1, x2, etc., and we end up going all the way up to xn. So all of these strips have a value at each end of x0 and x1, or whatever number we're at that point. And so we can say the total area of all the strips summed together, Sn, is equal to the sum from j equals 0 up to n minus 1 of f of xj times by delta xj. So to break it down, f of xj is just our strip height, and we can see that by thinking, well, if our j value is 3, our rectangle height, so x3 is this one, it will be this height, that is the rectangle's height because it's from the left side, and the area of this strip is therefore that times by this distance across, and that distance is represented by delta xj. So an additional equation to this would be where delta xj equals x of j plus 1 minus xj. So for a j equaling 3 example, j plus 1 is x equals 4, which is here, minus x equals 3, and so that would be our distance across, and we've times by our f of x3. If, for the example, the rectangles were in fact this way around, and we're counting the whole area above, we'd be looking at the height from this one instead of this for our first area. So it'd be f of x j plus 1 in that case, but we're not. For the first example, we're looking at this, and that is our total sum. And intuition leads us to expect that Sn will tend to A as our number of strips n tends to infinity. So if you imagine all of these strips, you get more and more strips piled in, they get thinner and thinner areas like this. That blue shaded area, or error in a sense, the discrepancy from our true area under the curve, will keep getting smaller and smaller as n tends to infinity until it would vanish in that limit. It's what our intuition says. So what Riemann did was he generalized this intuition and showed that it is in fact correct. So he looked at the upper and lower sums, external being these rectangles, as I showed before, and internal being the ones that are currently shown. Those rectangles provide an upper bound and lower bound to the sums we would get from this rectangular form of finding the area. So he did that for both cases and found that they have the same limit as n tends to infinity. So instead of using just upper and lower bounds for these values of height, so this is the lower bound where it's xj, and this would be xj plus 1 for any of these strips, so xj plus 1. You could use any height between those two values. So it could be xj plus a half, for example, would lie there, and it's just whatever the function is at that x value. So what Riemann did was he said, well, the height of a strip, which would be f of, and now we'll use a different variable instead of x to represent it, so psi j, and that's where psi of j is any point between xj and xj plus 1 inclusive. So what Riemann did would, he found that the definition that we used before, if we now use our height to be this psi j, would be this new Sn star, to represent this a different Sn this time, would be between j equals 0 to n minus 1 of f of psi j delta xj. So let's say it was our fxj plus a half, that example where we're using this height. It won't be this rectangle, and it won't be the rectangle above that where it's the upper bound. It will be halfway between, and you could show for any height of rectangle that we use, as long as we're consistent for the height that we're using for all strips. He showed that Sn star tends to Sn that we had initially, so just this simple xj, also tends to our area under the curve as n tends to infinity. And this is a general finding. It formalizes our intuition. And so we say that this integral of our function f of x between a and b is the limit as n tends to infinity and therefore dxj tends to 0 of the sum between 0 or j equaling 0 and n minus 1 of f of psi j delta xj. And that would be our definition, and it's the integral of x between a and b. So in this case, as we've defined the edges of our integral, it's not just left to interpretation. We have a and b as our values. This is known as a definite integral. To go into some more details before we properly investigate what integrals are, we'll be defining some nomenclature and just looking at some different things here. Let's start with the nomenclature. So we might say, firstly, that f of x is known as the integrand of our integral. So it's what we are integrating is known as the integrand. And a and b are known as the lower and upper, respectively, limits of our integration. And here, x is just a dummy variable, is what it's known as. So what that means is we can use any variable in its case, and it will mean the same thing. So it would be like saying the integral between a and b of our integrand f of x dx, that's exactly the same as the integral between a and b of f of s, let's say, ds. That's the same as, again, between a and b of f of q dq. As long as we're integrating over the same variable, we just change it accordingly, and it's just known as a dummy variable. You could call it anything you like. You could call it, I don't know, glass of water. F of glass of water, d glass of water, that would be our integral, and that's our dummy variable is glass of water there. So it really doesn't matter, but use what you feel is appropriate at the time. We also define that an integral between a and b of our integrand f of x dx is minus the integral from b to a of f of x dx. And the way you can think about this is just you're basically reversing the strip summation and working backwards on it and it will be a negative area in the sense that you're just working from b down to a, and that will get a negative integral, and we define it in this way. And hence, if you had an integral of a to a of f of x dx, this has no area under the graph. If you were just doing at the point A, it's infinitely thin, so you're going to have no area, and that integral will just result in 0. And finally, areas can be added or subtracted. So this is the same as saying integrals can be added or subtracted, because addition rules for areas is the same as that of integrals. So if we wrote it in a mathematical form, this would be saying like the area under the graph f of x between a and c, so the integral of f of x between a and c, is the same as the integral from a to b of f of x plus the integral from b to c of f of x dx. And this is very helpful. You'll see much of this later on, of splitting up these integrals into different components. And similarly, if we just looked at it in a graphical sense, the area under the graph from a to b is the same as the area under the graph from a to c minus that of b to c. And that would be the same as just minusing this term onto that side. And this rule is always true. It's just you need to get into your head that integrals are just representing areas. Today we have briefly looked at what integration is and seen how Riemann found an answer for finding the area under a curve. In the next video, we'll be looking at the fundamental theorem of calculus, i.e. how integration relates to differentiation. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.